Thank you, Fritz, for the very kind introduction. Thanks to HITS for welcoming me this year as a HITS professor. I'll talk about 4 seasons of renewable energy. This is my 3rd season in HITS. I came in the spring, summer. That's my autumn visit. I'll come back in winter, just before Christmas, for the workshop organized by Fritz, and also come enjoy the Christmas market. Okay, so in my talk, I'll answer a few questions. I'll start by answering the question, why study stars and massive stars in particular? Then I'll describe, hopefully in an understandable fashion, how to model massive stars and predict their fate and how they shape the universe. Then I will look in as well at how to assess the impact of rotation. And then it looked like I could retire and that my previous PhD supervisor could retire now. But no, the next question will be one now, one next. And then what else will look at renewable energy research I started doing as part of the Digital Society Institute. Okay, so starting from the importance of massive stars. Massive stars have several key roles in the universe. They provide radiative, kinetic, and chemical feedback. Radiative because they are very luminous. They can be more than 1 million times more luminous than the sun. Kinetic through their stellar wind, so they have a lot of, they actually quite have a nice life. Massive stars, they lose mass over their lifetime rather than humans, us generally gaining weight over gaining mass over our lifetime. And then they produce chemical elements. I'll mention that, how we can study that in stars. And the other advantage of massive stars is that they're very short-lived. So the lifetime of the sun is roughly 9 billion years, and the sun is a middle-aged star, whereas massive stars only last a few million years. So what happens is they can be born as with the first stellar generations, only 400 million years after the Big Bang, shown on the left, and then impact the universe from that point all the way up to now. And while the stars that were born at this stage are all dead and disappeared, the explosions that they produce can be visible up to quite high redshift. So we can witness nowadays explosion of massive stars from this point onwards. As I said, from that point onwards, massive stars have this continuous and important feedback on the evolution of the universe and galaxies around them. We are also very interested in answering the question what stars we are made of, where all the chemical elements that we have around us come from, in which stars. And I like to have the Karlsruhe version of this plot so that you see some German words. So this plot is the nuclear chart, which is an enhanced version of the periodic table. You're probably used to the periodic table. So with number of protons in the periodic table only. But in this case, in nuclear physics, we also care about the number of neutrons on the x-axis. And we start the periodic table will roughly follow the black dots here, which are the stable nuclei, as we call them. And then we can follow in these charts various processes in different types of stars that create different chemical elements. So we start from hydrogen at the bottom, so just one proton, all the way to iron. This is done via fusion processes inside massive stars in particular. And above iron, the Coulomb repulsion, so electrostatic repulsion, is too strong. So the only way to go beyond iron all the way up to lead and further is via so-called neutron captures. And this can happen through the rapid R neutron captures relative to beta decays, or the slow S neutron captures that follow the value of stability, which is in black here. So these are famous processes. The R process is where, for example, uranium or a lot of gold comes from. So we're interested in that. S process is quieter, but nevertheless produces half of the elements above iron. And I've been busy over the years studying slight variations of the S process called the weak S process. Weak because it doesn't go all the way to lead here, but stops at around strontium. And this is happening in massive stars. In some cases, we don't know how far it goes. And most recently, I've started getting involved in I process, I for intermediate, because somewhere in between the slow and rapid neutron captures. But in general, we want to know where chemical elements come from, and mostly it happens in stars. And finally, even though exoplanet research is a more recent and very hot topic, our understanding of exoplanet is reliant on our understanding of stars. So generally, exoplanet signals is 1% to 0.01% of the signal of the star that we observe the planet through or in front of. And therefore, if you don't know what's happening at the surface of a star, like convective stars, which is often the case for low mass stars, you cannot really study the exoplanet that goes around it. So this is not a quote from me. This is a quote from exoplanet researchers that have to care more and more about stars. Okay, so hopefully I've convinced you that it's worth studying stars. Next question is, how can we model stars? So if you've followed a course in astrophysics, you would have learned generally the stellar structure equations, but basically it goes back to the conservation principle in physics. Quantities that are conserved are mass, energy, and momentum. So these are three equations that we take from general physics, and then we add a fourth equation, which is energy transport, and this gives us the general equations we use to model stars. But in addition, there's a lot of other physical processes happening. As I talked about nuclear processes, there are lots of nuclear reactions taking place in stars. Mass loss, as I said, is a nice feature of massive stars, and it's critical, as I will show you today. Then we have processes like convection, rotation, magnetic fields, binary interactions, equation of state, opacities, neutrinos. So there's a lot of physics to study in stars, and we can both learn about stars, but also about those processes by studying stars. And also what we mean by metallicity dependence, that's how the processes, all these processes and the structure of stars depend on when the star is formed in the universe. Is it in the early universe, or is it more like nowadays? Now we've been running, scientists have been running what we call stellar models for decades. And in order to run these simulations on computers, let's say 50 years ago, people had to make the simplifying assumption of spherical symmetry. So even though a star is a ball, so has 3 dimensions, we can assume that most quantities are roughly the same on concentric shells. So for example, the temperature is roughly the same on a given sphere. And that simplifying assumption means that we can treat everything as a function of radius, so from the center to the surface, and we would have a constant temperature at a given distance. So that makes our models so-called one-dimensional, just as a function of radius, and it drastically reduces the cost of simulating those models. And those models have been extremely successful. They can predict, as I will show you, the structure of the whole star throughout its whole lifetime, and therefore determine the impact, can provide theoretical framework of interpretation of large observational surveys, and for example, observations of supernova, also creates a bridge between astronomical observation and nuclear physics experiment and theory. So as an example, I'm going to take you through quite a complex diagram, but it's my favorite diagram. So my goal is always for people to understand this diagram better after my talk than before. So I call this the CV, so curriculum vitae of a star. It summarizes everything that's happening in a star from the time it's formed until the moment it's going to die as a supernova, neutron star, or black hole. So if you follow me, I have to stay on between the yellow lines. So we start, time moves from left to right. And then the bottom is always the center of the star. The top is the surface. And you follow the mass coordinate. So this is for a 15 solar mass star. So a star is 15 times the mass of the sun. And you see colorful zones. But in general, as we move to the right, we move forward in time and always have the center at the bottom, the surface of the star at the top. I don't have to worry necessarily about all the details, but all the colorful zones, whatever the color, are zones where the gas is turbulent. It's a process we call convection. Importance of convection is wherever it takes place, it very efficiently mixes the chemical composition. That means you can replenish the fuel, which often takes place at the bottom of a convective region, or you can enrich the surface. If you have a convective envelope, you can bring material that is processed deep inside the star all the way up to the surface, and therefore enrich the interstellar medium with this material. And one of the key points here is to show that convection occurs throughout the evolution of the star in different parts, and therefore convection is quite important. Now, if we move into some details, we can follow some letters. So this is H for hydrogen, helium, carbon, neon, oxygen, and silicon. And these are the burning stages that massive stars go through before they end up with an iron core, at which point you can't extract enough nuclear energy anymore. At that point, the core will collapse and form either a supernova explosion or a neutron star or a black hole, and I'll come back to that. And then this red box now highlights the inner part of the star, and this is the part of the star that's called the carbon-oxygen core. And this is the part that will take part in the late phases, or these advanced burning phases, will also be critical for the type of remnant that will be produced, either neutron star, black hole, supernova, or not. So remember, I'll talk about CO core mass quite a lot. Just remember, this is this inner part of the star later on. And then the time axis, you just need to remember that acceleration speeds up. This is now the log of the time left. So here 6 means a million years. As I explained, the lifetime of a massive star is roughly millions of years. As you move through the burning phases, evolution accelerates. This is now 1 year. This is now roughly a day, and the explosion takes seconds. So this is why we need to use these special time scales to follow the evolution. It also means numerically, it's very challenging because you have a wide range of time scale from billions of years to seconds. But also in terms of length scale, you might not have noticed, but these black lines here with log of r, this is the log of the radius in centimeters. Why not use centimeters? And you can see the inner parts are 10 to the 7 centimeters, so you're talking close to a kilometer. And then 10 to the 13, that's the distance between the sun and the earth. Okay, so these are a wide range of time scales, length scale as well. So it represents a big challenge to model those stars in terms of range of time scales, range of length scales. Okay, so as I said, I'll talk about the CO core mass. So not only we can simulate the entire structure of a star throughout its life, we can do that for stars of different properties. So key properties of a star is its mass. So reference will always be the sun, 1 solar mass. So with 1D models, we can create a large grid of models from roughly the mass of the sun to at least 100 times the mass of the sun. So you might think, why do you bother calculating a star with 100 times the mass of the sun? They are now observed in the universe, so it's worth going so high. And also we use capital Z for metallicity, not redshift. So Z equals 0 for stellar evolution is early universe, the Big Bang, all the way up to what we call supersolar, is the current day. So the calculations, one model for one star takes hours or maybe a few days on a computer, any computer. But now we want to calculate large grids, and you need to understand what's happening in the code. So then the code crashes, so you have to restart it. So that's a long excuse to explain why we had the first paper in 2012 and last paper in 2024. So it took us over 10 years to complete the grid of models. But I don't know if you can see the number of citations. The first paper has been cited now nearly 1,600 times. So it shows the importance of stellar model in astrophysics. But now that we've completed that large grid of models, we can go and analyze and try to look at the fate of stars across the universe. Before I can do that, I just have to review the different types of supernova explosions. So I'll be quite brief, but hopefully I'll give you a good overview. So what happens with supernova? A new bright thing occurs in the sky. Telescopes detect it. They think it's a new supernova. And then theorists try to explain it. So there's slight variations in classification from observations and theory. This is the theoretical classification where we look at what is the engine behind the explosion, what drives the actual explosion. So Fritz, as you may already know, studies type 1a supernova. And then these are thermonuclear runaway in low mass stars. It can be single degenerate, double degenerate, various classes nowadays. You can ask always Fritz about this. I'm interested in the others, electron capture supernova, which are also studied here by Fritz and, for example, Alex. And this is kind of like the least massive stars, so around 8 and 9 solar masses. This is where the matter becomes so degenerate that you can have a process called electron capture that leads to the collapse of the star. And we're still not sure how they explode, but that's what Alex is working on. Do they produce normal core collapse, or do they explode as a thermonuclear explosion? Then we have a large group called core collapse, or generally iron core collapse. This is following the previous figure I've shown you. You go through all the burning phase up to silicon burning, you produce an iron core, you can't extract enough energy from nuclear reaction. It collapses until neutron density, so until densities are so high that you have a stiff inner core, then the further material tries to accrete on the core, bounces, it launches a shock wave that sometimes successfully ejects the rest of the star. So that's a kind of like what we expect for most massive stars to have a core collapse. Supernova driven by, revived by neutrinos. As I'll show you, if you go up in initial mass, we'll form black holes. And if we have something that has never been seen, so sometimes called a theory spec, because only theoreticians are interested in the so-called pan-stability supernova, but I'm one of them. So what happens here, this is the other extreme compared to electron capture supernova. These are very massive stars, and they get so hot that 2 photons can annihilate and produce an electron-positron pair. And that reduces the pressure, leads to early collapse, and a thermonuclear runaway during oxygen burning stage. And that produces in some cases, very bright explosions. And I really hope James WST or James Webb Telescope or other telescope will finally see them in the early universe. Okay, and then you have more exotic engines like linked to magnetic fields in particular called magnetars and collapsars. If you just remember core collapse supernova, pan stability, they will appear in my figures later. Okay, and then the alternative is you can have direct black hole formation, which I'll come back to. So now I've told you how we can model stars, how they evolve. The next question is how can we determine the fate of massive stars? So in my dreams, I simulate stars and the explosion in 3D MHD simulations. In practice, it's not happening. It's never going to happen, unfortunately. That's why I still dream about it. Because as I hopefully described to you, the 1D models for the large grids, we need to simulate not just one star, but let's say thousands of stars for over a lifetime of millions of years or longer. And I talked about different processes. The shortest processes are of the order of seconds or minutes or days. So we'll never be able to do stellar evolution all in 3D, even though we're making great progress, as I will describe later on. So for the evolution part, for large grid, it's only going to be possible in 1D. We're never going to be able to do it in 3D. However, once we've reached what we call the collapse stage, this iron core, we are now have enough computing power to do the explosion part in 3D. So there's a number of groups, which I've listed key names here. And in that context, I want to point that we also translating 1D progenitors, so these 1D stellar evolution models, into 3D initial conditions. We've just submitted the paper. We have minor corrections, so I'm quite hopeful that by my next visit in winter, this will be accepted and presented at the workshop. So this is providing 3D progenitor information for 3D supernova simulation. Okay, so that would be the kind of what we can do now. But it's still very expensive because most supernova groups do maybe a handful of 3D supernova simulations per year. So if we have a large grid, thousands of models, it's going to take still a long while to have 3D information. So we can't have 3D explosions for all of them. So what have people been doing over time? Well, they've done several levels of approximation. Some are called piston or thermal bomb, where you just inject enough energy in the center of the model, and you see what happens, what comes out, and you compare that to observation. Others have, for example, Fabian here is following the concept of entropy to try to determine the fate. In this talk, I've introduced the CO core mass, carbon, oxygen core mass, because we can use detailed 3D simulations and all these other methods to come up with a plan or a fate predicted according to the CO core mass. So let's look at how this is done. So this is done work from Fabian Schneider, who is here. So he looked at different stellar models. So you see here the list of different models. So these are single stars. Case A, B, C are different types of binary stars interacting at different time in their lifetime. And what you see is that if you compare their properties. So for example, in this case, compactness. How compact is the inner part of the star as a function of the CO core mass. The curves and the pattern looks quite similar between very different models. If you plotted this curve as a function of initial mass, it will look totally different. But this plot confirms that it's reasonable to use a CO core mass for different types of models. And therefore, we come up with kind of a prescriptions, or what is the prediction? If the CO core mass is smaller than a certain value, then we predict a successful core collapse, supernova explosion, so this neutrino-driven explosion, and we end up with a neutron star. Then there's an area where it's still quite uncertain what happens to the star. It could either be a black hole or a neutron star in a certain mass range, which you'll see later. And then above that, most people would argue that we produce a black hole, no successful explosion. And then for me, what is most interesting is we then enter the phase of pair instability supernova, where we still haven't observed them, but we still predict them from theory. And above that, we are back to black holes, which are above this mass range is least interesting for stellar evolution, but it's still very interesting for providing seeds to supermassive black holes that are observed in galaxies at higher and higher redshift. Okay, so jumping now straight to the final result. The x-axis is the metallicity. So this follows the second figure I showed you, where you had the Big Bang on the left. So just imagine Big Bang on the left, now on the right, for different metallicities. And then the y-axis is the initial mass. So this is the least massive star to the most massive stars. And we can then look at what remnants, so neutron star, black holes, or pair instability, which have no remnants, do we expect from massive stars across the entire universe. So we can divide this figure into three parts. If you have massive stars that are not too massive, you're in the bottom part. And therefore, most massive stars are going to end up as neutron stars and have a successful core collapse supernova. If you go up in mass, the fate depends a lot on metallicity and mass loss, because mass loss is driven by interaction of light with the gas inside the star. And this interaction depends a lot on if there are metals or not, so especially iron inside the star. If you have lots of iron, so you're at high metallicity, a lot of possible ways for light to interact with matter, and therefore you can lose a lot of mass. So if you've noticed, there are some white contour lines. These white contour lines denote the total final mass of the models at the end of the evolution. So in our nearby universe, you can a star can be formed with 500 solar masses initially. It will end up with only 30 solar masses because of all the mass it's lost over time. So therefore we only predict black holes at high metallicity. If you go down in metallicity, mass loss goes down, so stars can retain enough mass. And there is a parameter space, which is low metallicity, so early universe, where this pair instability is rare type of supernova can take place. So now this, if you notice, there's omega equals 0, that means non-rotating model. Then we can play a game of spot the differences. So now this is the same figure, but omega is larger than 0. So these are models that take into account the fact that stars rotate. And you can see, let's see if you spot difference. So this is rotating, non-rotating, rotating, non-rotating. So last one on rotating, you can see that the black area here has become much larger. And this is mostly due to the fact that if a star rotates, it's generally going to lose more mass. And therefore, it's going to have a larger fraction of very massive stars that lose enough mass to just produce a black hole at the end of their life. It pushes the pair instability region to lower metallicities. That might explain why we have not observed pair instability supernova yet. So that's still my hope. And then you have other few detailed feature. But basically, it shows that with 1D models, we can model the entire structure of stars across the universe and predict their fate. And we can also look at different properties. These are now observing types. So type 2 have high gen in the spectrum. Type 1b have no hydrogen, but they have helium in the spectrum. Type 1c have neither hydrogen nor helium observed in the spectrum. You can see that we can start predicting more and more properties of the supernova. Then we can play with the IMF, the initial mass function. So depending on how many stars are born with 1 solar mass versus how many stars are born with 100 solar mass. And you can see also the effect of rotation having on these processes, and then the fraction of neutron stars, which are 70% in this case, and different supernova types. So I won't go into more detail. But as many of you would have followed, we are now not only able to observe supernova and neutron stars, we can observe more and more black holes. And that's very interesting for us because at least half of the diagram I've shown you looks at or has predictions for black holes, and before we could barely constrain these predictions with observations. Now this, in the vertical dimension, you have the masses of black hole observed, and then our x-axis has no resemblance, but you have different systems. So in a gravitational wave observations, you have two black holes that merge, produce a combined object that is more massive and bends space-time, and this is what we observe in gravitational waves. And in particular, a key question in this field of study is there a black hole mass gap due to the parent stability? So this parent stability explode, eject the entire material, have no more remnant. So the prediction from the models is you have no black holes between roughly 50 initially to 150 solar masses. But then you look at this object already, you see that it's in the so-called black hole parent stability mass gap. And most recently, the collaborations announced the gravitational wave 231123 with black hole masses of 137. This is possibly above the gap, and 100, which is depending on what gap you assume, right in the middle of the gap. So then as theoreticians, we then have to think, can we explain these black hole masses of roughly 100 solar masses or not? So now we've used the same models I've described to you before, but now different colors correspond to different metallicities. So you see the value of metallicities in Z here, again from least most metal poor in the early universe to supersolar. As I explained, if you're at high metallicity, mass loss is so strong. So this is, for example, the purple curve. You see that whatever initial mass you start with on the x-axis, you finish with roughly 30 solar mass black holes. So your maximum black hole mass at high metallicity is about 30 or 50 solar masses. Whereas if you go down in metallicity, so earlier in the universe, then you have less mass loss. And in our non-rotating models, we have maximal black hole mass just under 100, so it's 92, which can explain the latest observation of GW 231123. You might think that if stars rotate, it can improve the situation. But in this case, it makes it worse. Note that the y-axis has now shrunk to 60. In rotating models, for reasons I can explain later, we cannot retain as much mass. So we predict lower mass for rotating models than for non-rotating models. But in general, we can more or less explain this, the most massive black hole below the gap that we observe. Okay, so this is the point where I retire and we can all go home because we have 1D models that can predict the structure of star, the evolution, can compare to observations. Obviously, it's still only 234, so the talk is not over. So the question is, what next? What do we need to improve? So as I explained, there's a lot of interesting physics inside stellar models. So first of all, we could say, well, we just want to understand or study those extra physical processes. I've mostly talked about rotation so far. I'm going to talk about convection next. Andreas Sander, who is at ARI, I'm going to give a seminar on Thursday. He's going to tell me correctly that the mass loss prescriptions I use in the models are outdated. And then Fabian Schneider and others would tell me I have not considered binary interactions. That's an interesting aspect because when you consider binary interactions, you need to at least introduce two more dimensions. You have the mass ratios of the two stars, the orbital separation, and potentially eccentricity. So you have a lot more models that you would want to calculate, which becomes a big challenge in its own. But the last part of my talk will be just focusing on convection and a little bit on magnetic fields. And why do we need to worry about convection? Hopefully the first sentence summarizes it. If, depending on what choices are made for convection and what we call convective boundary mixing, we have a 70% uncertainty in the predictions, and it can be translated into a 15 solar mass star or model behaving like a 20 solar mass star or model. So for certain people, that's good enough, but for most people, that's not good enough. What's interesting, and Saskia Eke's group works on asteroseismology, is we can use asteroseismology as well as upside motion to constrain the inner structure of stars on the main sequence, and therefore improve the treatment of convection in stars in the early evolution. But we still need more constraint for the late evolution. Furthermore, if we go to the early universe, we have cases where different burning stage interact. So I'll show you some examples later, but there are two main categories. Some where hydrogen and helium burning regions are connected by convection, and you have unique nucleosynthesis, in particular primary nitrogen. I don't know if some of you followed the JWST observations of nitrogen-rich high redshift galaxies, which are hard to explain without such mergers. And we can also influence the CO core mass. So I explained the importance of the CO core mass. This determines kind of the fate. So this hydrogen-helium shell merger can therefore change the fate and the location of the mass gap. In the late phases, we can also have what we call carbon, neon, oxygen shell mergers. I will show you some animation in a bit, so I won't talk too much. But they can also change the explodability of a star, whether you have a successful or failed explosion. So how can we improve the treatment of convection? This is one particular case where 3D hydro simulations can really help. And this is why I entitled The Dawn of Multistellar Modeling, because we now have enough computing power to do at least a fraction of the lifetime of the star, a fraction of the star with 3D simulations, rather than just relying on 1D model. And this is an incomplete list, but the idea is you have the CV of the star, which is the evolution of the structure in the background. And for each burning phase, you see there's at least one study that studied that phase in 3D hydro simulations, whereas let's say all these citations are in the last 10 to 15 years, and increasing power carries on. And also Robert Andrassi, who is here, led a code comparison. So we even have code comparison to benchmark our simulations between different teams, which is very important for reproducibility. Okay, so how do we go about improving the 1D models with 3D hydro simulations? Well, we start with a small fraction of the structure evolution diagrams I've shown you, these large diagrams. We pick a small region here, so we do a zoom in, and then we're going to we take the structure of the star at between two radii, we put it into a 3D computational domain, which looks like a Rubik's Cube. If you like Rubik's Cube, you can check out my son's YouTube recording of solving Rubik's Cube blindfolded, which is still hard to believe. So basically, convection in 1D model is assumed to occur between this point and that point, but then in 3D hydro simulations, you can actually see the turbulence taking place in action directly. So this is a difficult step, but actually the most difficult step in what we call the 3-2-1D loop is not to go from 1D to 3D, but then to interpret the 3D results with some theory that enables us to generalize the results of one 3D simulation over the entire lifetime and entire structure of the stars by going back to 1D model. So in our case, we've worked on what we call the entrainment law, which is shown by those curves here. I'll skip that, but I wanted to mention Robert Andrassi and the team here have done similar models to gain insight into improved 1D models. And this is our examples where we use some theory, which I won't go into. But the advantage of using theory is you can benchmark or calibrate the free parameters of a theory and then generalize or use that equation in all stellar models in 1D, not just the exact case that was studied in 3D. If we do that, we use some prescription, we compare to observations, we can then do a second generation of 1D models. This is work by Federico, who is now here at HITS. And you see the cyan part, the blue part is kind of like what traditional models were doing with convection. The cyan part is the extra mixing, what we call convective boundary mixing, that we've added to the 1D model to better reproduce what's happening in 3D hydro simulations. And we can go back to our second loop. So we pick one region, which is this one, zoomed in here, zoomed in here. And then we go back to the 3D hydro simulations. And then we reanalyze it with theory. And we hope that where these two lines nearly touch each other, that we have reached convergence. So by going through this 3 to 1D loop, we keep improving the 1D models until they agree with the 3D model. What we also see is the fact that I mentioned that we have shell mergers, so different burning phases interacting with each other. In this case, a carbon, neon, and oxygen burning layer starts interacting with convection, and we can then study that in full 3D hydro. So here, this one, the inner ring is the oxygen burning ring. The intermediate ring is the neon burning region. And the outer region, this whole region, is burning carbon. And what happens after a short while, after the start of the simulation, is that the neon and carbon burning regions are connected by turbulent motion. And when this happens, then carbon is brought to a temperature where it shouldn't exist, and therefore it burns very fast and leads to very energetic turbulence that drives a very turbulent flow. And in the 1D models, we see carbon, neon, oxygen, all three regions interact. What I'm going to show you now in a zoomed in version. By the way, if you're wondering what the donut is, this is a top view of a computational domain. So these movies are slices through the equator of a simulation. Now this is a zoomed in, so you have oxygen burning region here, neon burning. We only see the bottom of the carbon burning region. And we can see how the division between carbon and neon burning disappears quite quickly. And then you'll see the flows from the top reaching the bottom of the neon burning shell. Then in the first few 3D simulations, the resolution was not high enough that the entire domain would become convective very quickly. But what you see here is even though the convection is very turbulent, very energetic flows, the inner ring stays stable and resists the turbulent flow boat. So this is also a sign that the 1D models and 3D models are converging, because we no longer have 3D simulations that become fully turbulent everywhere. I'm still puzzled why is the inner part of the model not becoming turbulent. Okay, so this is now to summarize this part. So we have our summary plots, we call sometimes Kippenan diagrams, that we have where we have improved the treatment of convection with the cyan color. They produce shell merger. And for some of you, if you've learned the onion-shaped structure of supernova progenitors at the time they are about to explode, this picture might need to be revising. And if you will have work in preparation, Emily Whitehead, my PhD student, is supposed to submit the paper today. So I'll check with her later. And Aisha Arun, a PhD student in Edinburgh, is going to calculate the nucleosynthesis of those new models. So there'll be lots of updates. I have two more short topics for this talk. First one is looking at nuclear astrophysics. So what can we do next? So Giovanni has been developing the Phlegathon code. I won't tell you too much about it, but hopefully come back to a point that Corina, as a master student, was going to implement GPU offloading into that code. And we started discussions today. What are we going to do with this code? Well, we can do nuclear astrophysics and study magnetic fields. So on the left-hand side, the color represents oxygen composition, oxygen mass fraction, and we can look at asymmetries in the nuclear processes and composition inside the star. And the right-hand side shows magnetic field lines. So we're going to see how turbulence interacts with magnetic fields inside of stars. So more to come from that. Okay, so the last question for today is what else, which is quite significant fraction. This is where I introduce the slide. Keele is not Keele, but where is Keele? So you have a map of England here on the left, and then the zoom in, here you have Birmingham, Manchester, and Liverpool, and Keele is kind of in the middle of those regions. If you like potteries, you might have heard of the Wedgwood blue pottery. This is where the area is called the potteries. For those who like football, it's where Stoke City is, the city of Stoke-on-Trent. But what is more exciting from my point of view is the campus is a living laboratory. So we have 2 wind turbines and 12,220 solar panels. So that enables us to produce half the electricity we consume on campus as an average throughout the year. We also have, I'm director of the Digital Society Institute. We have data visualization suite and other toys. I more or less have a new toy to play with every month. And then this one is not my toy yet, but hopefully one day. It's a hydrogen-powered tractor, which is developed by JCB, and they're down the road from us. So some of you may know I grew up on a farm, so now I'm reconnecting and hopefully driving a hydrogen-powered tractor. A few years' time, I just have to convince them to give us a tractor. But more seriously, what we can do is, so within DSI, which is quite similar to HITS, interdisciplinary research. So the vision for Digital Society Institutes to enable scientific breakthroughs and societal transformation via responsible AI, data science, and digital technology. And you can follow all our updates on our LinkedIn page. And the digital transformation affects all aspects of our life, private, businesses, research. But one theme that I'm leading as part of DSI is the digital sustainability and renewable energy. So if you're interested, you can maybe take part in the quiz. The answers are given at the end. There's no scoring, so you have no risk. But it's interesting to see what people think about renewable energy. And then there are 2 aspects of digital sustainability. One is how to make digital infrastructure sustainable, and the other one is how data science can help drive transition to sustainable power generation. As part of that, we have what is called green HPC. We can call our HPC green because our electricity comes from renewable energy. And the idea of green HPC is to have a hybrid architecture. So we have traditional CPUs. We have actually 2 types of GPUs, Hopper 100 and Lovelace 40. And the Lovelace 40 are actually more efficient for AI workload to be discussed and to be compared. But the idea is that we have this 3 architecture. We can compare how different codes run more efficiently on one or the other, which code has the least CO2 footprint. And if you don't know Ada Lovelace, I encourage you to learn more about Ada Lovelace, which the name was used to name the Lovelace 40 cards. And as part of that thread of work, I'm developing a training material called Deep Dive as part of the DIRAC UK HPC consortium. And I'm going to work with the team here. So if more people are interested, let me know. The newest toys are linked to hydrogen. So if you want to know more detail, we have a project page called HYDEX. As part of that, we now not only have renewable energy production, we have an electrolyzer. This is the picture of the refueling station. So we have a hydrogen electrolyzer, hydrogen storage, a refueling station, and 2 hydrogen cars, Toyota Mirai. Soon the hydrogen tractor, but that's still work in progress. As part of what I call the living laboratory, we have many pieces of the puzzle for the renewable energy transition on campus. I tested the live feed. This is a snapshot from our live data feed. I can maybe make it work later on, but it doesn't work at the moment. But this is the import from the grid. Then we have our 2 wind turbines that produce some power. We have our solar panels. It's England, but there's still a lot of solar power in England. Unlike what people may think, it's not that bad, the weather. And then this is the power consumption on campus. We also have a battery. As I said, we have the hydrogen electrolyzer. So we can study the detail of all the moving parts. We have monitoring of heating in buildings. So it's really advanced monitoring and technology development, living laboratory that we can use on campus. Just one example, this is a paper we're about to submit, work by actually an excellent undergrad student, George Abraham. And one of the things we've done with him is to predict how much green hydrogen we can produce over a year. This is for the year 2023. And this, we look at kilos of hydrogen using different size of batteries. So we have one battery on campus. It's a 2 megawatt hour, so it's the blue line here. But we wanted to test how much green hydrogen we can produce, assuming different size of batteries. So for example, should we add another battery on campus, or is it too large a battery? And by green hydrogen, we mean we use only the excess power produced on campus. So that's when the campus is producing more energy than what is consumed. If that is the case, up to now, we have to export this excess energy, excess power, and sometimes we even have to shut down the solar panels because we would be penalized harshly. Actually, maybe I can still show you. Here we have an export limit. And actually, most renewable energy sites that want to set up in the UK can't do it because the export limit is too tight, so they can't set up a new facility. But if instead of exporting, people are producing green hydrogen, then they don't have a problem with the export limit. So then they can move on and produce more solar panels on many more sites. And basically the short end of the story here is that our batteries is ideal for our case. Even if we were to have a battery that is twice as large, we wouldn't produce more green hydrogen than we can produce. You can see that we would produce 2 tons. And the general rule, this good number to remember, 1 kilo of hydrogen can drive a normal hydrogen car like Toyota Mirai 100 kilometers. So if you want go from kilos to number of kilometers we can drive, multiply by 100. There's quite a lot of kilometers we can drive hydrogen cars. So whenever it's possible, I volunteer to drive the hydrogen car. I went to pick them up the first time, went for a spin at the weekend. Okay. So here are my conclusions. So hopefully I convince you that stars are important, how we can use 1D models to study their impact and their evolution throughout the universe. I've also explained to you the 3-to-1D loop that we use to improve 1D models with detailed 3D hydro simulations, soon MHD. I briefly talked about the shell mergers and the potential impact they will have on explodability of stars. So this is the picture I've shown you for the fate is not the final one probably, and also for nucleosynthesis. What is exciting is we can use observations like asteroseismology as well as high performance computing to improve our models. And I've also briefly told you about energy storage, work we do on hydrogen, battery. I'm also pro-nuclear, and people want to discuss it in the audience or later. I'm happy to discuss this. And with the goal of improving energy resilience, minimizing carbon footprint going forward. Okay, thank you for your attention.